Hello students, in the previous lectures we had discussed limit of function at a point, and from the limit of function at a point we have come to the next topic of differentiability of function, continuity of function at a point, and discuss continuity of function, different functions at a point. And then if function was not continuous at a point, then we discuss discontinuity of function at a point, and different kind of and discuss different responsibilities and solve problem based on them. Now we'll take up the same concept of limit of function to the differentiability of function and discuss its theoretical interpretation. So the first principle you have read in the +2 class is the definition of derivative is based on the concept of limit. So we'll revise it and then solve problem based on that. You generalize this definition of differentiability of function at a point. So derivative of function at a point, let fx be a function with domain here. We are discussing fx is a real valued function. We are discussing the differentiability of function at any point of the domain of the function. Function and domain is the set of real numbers, the point at which the function is valued. Then the derivative of fx at a point x belongs to d is defined as limit x approaches to limit h approaches 0 of f of x plus h minus fx upon h. So this is the limit of this quotient function as quotient function of h, and we are finding differential at x. At x is any point of the domain. So we are discussing at any arbitrary point of the domain. This is general definition of this. Provided when will this limit, if this limit exists, provided if this limit exists and is finite. The function fx is said to be differentiable at x if this limit x equals to 0 of f of x plus h minus f of x upon h, if this exists, this limit exists and it is finite, then this value is denoted by f dash at x or ddx of f of x. So this is the ddx of fx. Now if in place of at arbitrary point we take any fixed point c, we will find any fixed point c of the domain of the function, then the and c is the any interior point. This c will not be boundary point, c the any interior point of the domain of function. If domain is open interval, then we can discuss all the points. If domain is a closed interval, then we can discuss it in the interior points of D. Then derivative of fx at c belonging to the domain. C belongs to domain. C must be the point of domain. C must be the point at which the function is well defined. Also defined and is noted by f dash c. In case of x, earlier we have found the derivative at arbitrary point x of the domain. Now we're finding a fixed point. F dash c is equal to limit x approaches to c. We are discussing it we are finding the limit in the neighborhood of c of fx minus fc upon x minus c, provided if when will fx have differential at c, provided this limit x equals to c of fx minus fc upon x minus c limit exists and finite. Then and only then fx is said to be differentiable at c. Right? If in the above limit x approaches c from negative, this x will c from negative, this is called left hand derivative. Left hand derivative at x is equal to c. And if x will c from positive, then we say right hand derivative of fx at c. So similarly, right, and they are noted by left hand derivative at c is written as f dash c minus h, or left hand derivative of f at c is equal to limit. This is the definition of derivative at c. Only the differences of limit x equals to 0 negative. So similarly, right hand derivative of fx at c is equal to f dash c at c plus 0, or we can write it right hand derivative of f at c is equal to Now again, this is limit of the this is derivative of f at c. Only the limit will be from c, which is f to c from positive, and the same ratio of the function f x minus f c upon c. Now, when will we say that the function is differentiable at a point? When we'll say if both the limits, this limit and this limit exist, then and only then this f is said to be differentiable at this point. So the interpretation of this is if the left hand derivative at c and right hand derivative at c both exist and both are equal and they're finite numbers, then we say that f is differentiable at c and equal to by f at c, which so in order to find derivative at c, we have to decide whether we have to find left hand derivative or right hand derivative, and both the derivative must exist and they must be equal. Then and only then we will say f is differentiable at any point c of the domain, at any fixed point c of the domain of the function. The process now we know that how to, we know that if function differentiate at the point, then both left hand derivative and right hand derivative at the point must exist. The process now, the process of finding a derivative function at any point of the domain is called differentiation. If you differentiate any function at a point, that is the process, the path we follow is called the differentiation. And the derivative form, this is called derivative or differential coefficients. This is called this is called differential coefficient of function f at c, and this is called differential coefficient of f at this is called differential coefficient of f at x. See, so from this we can come to this also. C x replace x by c or c by x by c or c by x. Now let's define derivative of a function in open interval or in closed interval. The function f(x) is said to be differentiable or derivable in an open interval ab of subset of domain of function f(x) if f(x) is differentiable or derivable at each point of this open interval. And function is said to be differentiable in a closed interval. Function f(x) is closed interval if f(x) is differentiable at each point of open interval and have right derivative at a and left derivative at b, then we say that the function is differentiable in a closed interval. Now let's understand what what is this, what is the geometrical interpretation of derivative at a point or differentiability of function at a point. Now for that, let's consider a function y is equal to f(x), this y is equal to whose curve is a p q a p q p, and p and q are two neighboring points whose coordinates are p with xy, p coordinate with xy, and p with xy, and q is with q, and q is with coordinate x plus delta x plus delta x, and y plus delta x plus delta x, and y plus delta x plus delta x, and y plus delta y. Right? They're two different. From p, draw pm perpendicular on x-axis and qn perpendicular on x-axis, and from p draw pl perpendicular on nq and complete, and from p join a chord pq and produce it to meet x-axis at r, and at p draw tangent pt which meets x-axis at 2, and the chord PQ makes angle theta with positive x-axis, and the tangent and P makes angle psi with the positive x-axis. Now complete the diagram and then find the value of PL and QL. PL will be PL will be equal to MN. MN is equal to OM minus ON. This is equal to OM is equal to X plus delta X minus X equal to delta X. And similarly, QL is equal to Qn minus Ln is equal to Y plus delta minus Y. So this is equal to delta Y. Delta Y. Now, from the diagram, now as Q approaches P, as Q approaches P, we can say that Q will P. Now this tangent, this secant will become equal as Q approaches P means delta x equals 0 or delta, we can say delta x is 0 or delta y is 0. As delta x is 0 or delta y is 0 or Q approaches P, this secant PQ will become tangent PT, or we can write as delta approaches as delta x is 0 or Q approaches P or delta is 0, then theta will approach to psi, means the secant will become tangent at P. So from figure now, as Q equals to this is equal to 0. Now the ratio of delta y, ratio of delta y upon delta x, limit delta x as Q equals to P, this will delta x will become dy upon dx, definition of differential here. Delta here. Limit delta x 0, delta y upon delta x is equal to dy dx. Now similarly, delta tangent of psi is equal to limit tangent theta q approaches p of tangent of theta. Then theta is the angle made by the secant. As q approaches p, this secant will become tangent, so this will give us. And similarly, as the q approaches p, delta x is 0. So this will be this limit delta x delta 0, delta x is 0, limit delta is 0 of delta y upon delta x is equal to 0 dx. From this, we conclude that dy dx at differential of function y equal to fx at any point xy of the curve y of the curve is the tangent of the angle when the line tangent line at P makes with the positive x-axis. From this, we will differential y to x is equal to tangent of psi. So if we differentiate a function at a point, will give us the slope of the tangent at that point. This implies if we differentiate a function at any point, will give the slope of the tangent at that point. Now from this we can conclude if the tangent will be parallel to x-axis, then differential y, if differential y to x at any point is 0, means tangent at the point at which you have differentiated the function y to x is parallel to x-axis. If it become differential y to x become infinity, or that is dx converse of this dx is to y becomes 0, then we say the tangent is parallel to y-axis. So if differential of x is to y equal to 0, in fact, anybody say if differential of x is to y is equal to 0, we will come to the conclusion that tangent is parallel to y-axis. If differential of x is to y is to x is equal to 0, then we say that tangent will be parallel to x-axis. Now let's prove a thing based on the, let's relate quantity with differentiability. Prove that every real function which is differentiable at a point of its domain is also continuous at that point. Is the converse true? What does it say? If function is continuous, if function differentiable at a point, we'll prove that it is continuous. But the converse of this is not true. If a function is continuous at a point, the function where differential will support the contradiction with the help of an example of modulus, function modulus or modulus of x. Now let us take fx be differentiable at C, domain of function f. So if f is differentiable at this point, now we'll show that fx is continuous at x equals C. So if f is differentiable, this implies f dash c is equal to limit x to c fx minus fc upon x minus c, and this and is finite. If this is differential point, means left hand derivative at c is equal to right hand derivative at c, both are equal and both are equal to the value of the f dash c. Then we say that f is differential point. Means if f is differential at a point x to c, means left hand derivative at c and right hand derivative at c both exist and both are equal to Both are equal and equal to the value of f dash at c and the value of this ratio. Now to prove that f is continuous at c. So if you want to prove f is continuous at c means you show that the left limit at c is equal to right limit at c is equal to value of center point. Left limit at c, the function f(x) shall be continuous at c if left limit at c is equal to right limit at c is equal to value of center point. Or that is definition, f is continuous c if limit x to c of x is to fc. So limit x to c, this implies this is the this when will this limit exist? Limit x to c fx, when will this exist? If left limit at x is equal to c at x to c exists and right limit x to c exists and both are equal to value of function, then function set will be set one. So we have to find the limit both elements. So this is a very related concept. If you don't understand the limit of function at a point, then you don't understand the concept of left limit at a point, right hand limit at a point, then you can't understand the concept of differentiability at a point. If you can't understand the concept of limit at a point, left limit at a point, right limit at a point, you can't understand the differentiability of function at a point. So they are correlated. In order to understand the concept of differentiability, you must understand the concept of limit at a point, then onto a point, then you can proceed to the differentiability of function. So in order to prove this, we'll prove that. So limit of constant function, limit of x to c of fx and f's container limit of x to c. Now taking limit x to c common from this, and this will in order to prove it, in order, in order to prove this, limit x to c of fx minus c is 0. So f is non-decision. So let's left hand side of something. The second left hand side, limit x to c of fx minus fc multiplied by we convert into differential. And where limit by x minus c and limit this is a function. So limit of product limit into this. So this become limit x to c of fx minus fc upon x minus c become f plus c, and the following function limit of x to c is equal to c minus c equal to 0. So this comes out to be uh, limit x to c of f minus c comes out to be 0, implies f is continuous at c. Hence, so that if function is differentiable at a point, then the function will be continuous at a point. Converse is not necessarily true. We'll support it with help of an example. If that is, if function is continuous at a point, then the function will be differentiable at that point. We'll support this, illustrate this with an example. Fx is equal to modulus x. Modulus x, we know the definition of modulus x is equal to x if x is equal to 0, and x minus x is equal to 0, and the graph of this modulus function, domain of this function, all the numbers. So the graph and function of the function. Domain of the function, this function, that is set of all the number. Doubtful point is 0, so we'll discuss the limit and quantity of modulus x at 0. Now then, so that f is continuous at 0, but not the so this is doubtful point 0. So let's find the quantity of discuss quantity function at a point. So in order to discuss quantity of function at x equals 0, we have to find the left limit at 0, limit x is 0 from negative of fx, fx is equal to modulus x, limit x is 0 from negative of modulus x is 0, make substitution, put x is equal to 0 minus x as x is greater than 0, as x is 0 from negative, x is 0, modulus minus x is equal to h. So substitute limit x is 0, replace the this limits x is 0 of modulus minus h, modulus of minus h is equal to h, so limit x is 0. Similarly, right limit x is 0, x is 0 of fx is equal to, substitute the value of limit fx, limit x is 0 of from positive of modulus x. Now again, make substitution, change the limit x is 0 of modulus x 0 minus h equal to modulus x. So left limit 0, right limit 0, and value function at 0 equal to 0 implies this left limit equal to left limit as x is 0 from negative of fx equal to right limit as x plus 0 from positive of x is equal to value function at the point, implies the function fx is equal to modulus x continuous at 0. Now we'll find the left hand derivative of function at x equals 0. Left hand derivative definition, limit is 0 from negative of fx minus f0 upon x minus 0. So again change the limit, make substitution, and change the limit. So limit x is 0 for negative of modulus x, right? So change the limit 0 of 0 modulus x 0 minus x 0 minus x h is equal to 0 minus x modulus of minus x is equal to h and minus 1. This is equal to minus of limit x 0 of h upon x cancel. We have the cancel factor. This is minus 1. Similarly, right hand limit x equals to 0. We have solved this problem many times. Limit x equals 0 for positive of fx minus f0 upon x minus 0. Now substitute the Euler function, simplify it, change the limit. We got limit x is 0 of in 0 minus x modulus of 0 minus x is equal to modulus x is equal to h, x cancel is equal to 1. So left hand derivative is equal to minus 1, right hand is equal to 1 at 0. So f the modulus function is not differentiable at 0. So implies continuity of function at a point will not always imply that the function is definitely thing.